So in the previous video where we just talked about this theory behind Diffie-Hellman key exchange algorithm, we used the analogy of mixing colors and somehow exchanging this secret color without actually exchanging it. So it's time for us to now get into a little more details in terms of how this is actually done using real numbers. So that's what this Diffie-Hellman hands-on exercise is all about. So the analogy we used talked about this common paint or base color you need to start with, and then we mixed our secret color with the base color before we send it to the other person to exchange the secret color. So in reality, this base color actually consists of three different parts. So the first part is this shared secret, and then the shared secret consists of two numbers. One is called generator, the other is called a prime number. So we represent these two numbers as G and P, as you can see here, and then those numbers are used in a formula, a mathematical formula, as you can see here. So G goes here and then P goes here. So G to the power of K mod P. So where K is actually our secret color in our analogy. So we share this G and P as our base color or common paint. So in this example, just to make it a little more concrete, we use this number P, for example, which is 13, and then the number G, which is generator number, which is 5. That's the number we are going to be using for this particular example. So now let's decide first your private key, the secret color in this case. So let's say your private key is now 3 or something, and it's time for us to actually mix the colors, especially the secret key, whatever the secret color is, and then prime number and the generator. So the secret key is now 3, the prime number was 13, and then the generator is 5. So we can mix the color using this formula here, where the generator is 5 and then K is 3 and mod P is 13. So 5 to the power of 3 is actually 125, and if you get the mod value of the 13, so by getting a mod value, what we mean by that is simply dividing 125 by 13 and then getting just the remainder value of that operation. The mod value is actually turns out to be 8 right there. So basically this number serves as your color to be sent to the other side in our analogy. And then so this is just one side, right? Let's say Alice. The other side has to do the same computation. So let's just assume that the other side used the secret key that is maybe 2 or something. So their public color to be exchanged will be still using the same generator, which is 5, right? And then now this K for the other side, let's say Bob is 2, and then mod prime number 13. So therefore 5 to the power of 2 is 25, mod 13 is giving you 12. So that's the public color to be sent to Alice. So in this case, Alice sends number 8 to Bob, and Bob sends this number 12 to basically Alice. So the final step here is mixing your secret color with the public color sent to you to actually come up with the ultimate secret color to be exchanged, the common ultimate color to be exchanged between you and your partner. So before we actually try to compute that final number, let's summarize the numbers that were used here. So for example, Alice in our example used her secret key that was 3, and the generator which was 5, and the prime number that was 13. And then Bob used secret key that was 2, generator, same generator. This has to be common between the two, right? So 5, and then the prime number is still 13. And the public color Alice produced using these numbers for Alice was 8, and then the public color to be sent to Alice by Bob was 12. So this was sent to Alice, and that was sent to Bob in this case as a whole. So the next step here is, for example, Alice mixes her secret color with the public color sent by, oh, it's a typo, Bob here. So in this case, Bob sent to Alice number 12, right? So all we're doing is you use the same formula but using different number for the generator. So the generator in this case is the number Bob sent, so which is number 12, right? To the power of the secret key of Alice is still 3, right? And then mod 13, same prime number. So let's see what this number is. So 12 to the power of 3 is 17, 28, mod 13. So the final number that comes out of this is 12. The remainder is 12. And then we can actually also look into what Bob is supposed to do. So Bob mixes his secret color with the public color sent by Alice. So the public color sent by Alice is number 8, and we are using it as our generator, and the key Bob used was number 2, as you can see here. So we will use power of 2 and mod 13. So this is a number, an easy number to work with. So 8 to the power of 2 is 64, and then mod 13, which gives you number 12. So as you can see, the end result is you successfully exchanged the secret color, which is number 12 for both sides. So now they know their secret number is number 12, but they never really exchanged number 12 as a secret key. The example is slightly flawed because it happens to be that what Bob came up with, his public number, is, I mean, it happens to be the same as the secret number, so this is not really a perfect example, but still you can at least see you still have the same number at the end. So we probably should avoid this sort of a situation in real life key exchange exercise, and in reality we actually use very big numbers, so the chance of this happening is very slim. So actually when you do your own examples, your own numbers, you just carefully follow the steps I just talked about in this video, and it would be nice to be able to do something like this with your partner and just trying to see if you eventually ended up with the same number, and I think that's what makes it more interesting. So one more tip is, although we were using very simple numbers here, I think it's better for you to use relatively big numbers to do this exercise, and getting the results of the computations could sometimes be tough, so I recommend that you use something like Excel to do the calculations, which will make your job much easier.